Do you know what a scientific model is? What is a scientific model? What is a model? It is a mathematical or physical representation that is useful in making the world easier to understand. In order to be a scientific model, it must make correct predictions. This does not mean the model is correct. In fact, there's a common saying in the science community: all models are wrong. But some are useful. I think it's the full quote. This is usually how it begins. So, we can think of the Bohr model like this. So the Bohr model is wrong, but it can be used to correctly work this out. If we look and just think of atoms as the Bohr model, as we go left to right, what do? We increase the charge in the nucleus. So we start with a small dot and we make it bigger, and add electrons to this ring. So as we go right to left, we make a stronger nucleus and add electrons to this ring. If you want to use the Bohr model to help you understand, you can make up a model and just assume electrons in the same ring don't affect other electrons also in the same ring. Or orbit. So what's going on as we go left to right? We're making the nucleus stronger. And only putting electrons and let me remove the word only, and putting electrons in the same ring or orbit. And as the nucleus gets stronger, the ring gets pulled closer. This is not what happens, but this is a useful model. It's not a correct model, but it is a useful model. It can be used to help you understand why electrons or atoms get smaller as you move left to right. Now then, if we have an electron here on the outside versus an electron right here, which is easier to pull away from the atom? The one that's really far away with a weak nucleus, or the one that's really close with a stronger nucleus? So here, it's easier to pull an electron from a ring that's further away with a weak nucleus. So this means it has lower ionization energy. Again, ionization energy is the energy required to pull an electron off an atom. While here is more difficult because stronger nucleus pulls the ring closer. So if you want to imagine atoms as just being a center positively charged nucleus with planets that orbit on specific orbits, electrons orbiting on a specific ring, you can. The purpose of a model is to be useful and to correctly explain the universe. As long as the model correctly makes predictions, it's alright. The model can be wrong, but as long as it's useful and correctly explaining things, it can be used. So let's go down. As we go down, what we end up doing, yes, the nucleus gets stronger, but we add another ring. So as we go down, nucleus gets stronger. So it pulls the orbits closer, but adds a whole new orbit. So as you go down, the nucleus gets stronger, pulling previous orbits closer. but also adds a new orbit that's farther away. So as you go down, atoms get bigger because you're adding a whole other orbit on top. Yes, the previous orbits shrink, but you're adding a brand new orbit. So the new orbits make the atom bigger. But which is easier to pull off? An electron that's very close to a weak nucleus, or an electron that's very far away? As you go down, the increased distance of the new orbital or new orbit makes it easier to pull off a new electron. This is because of distance, but mostly due to the inner rings, the electrons on the inner rings shielding the nucleus, meaning pushing the outer ring away. So all the electrons in these inner orbits are counteracting some of the charge of the nucleus. So this electron and these protons are being shielding each other. So this electron sees all these negative charges and the central positive charge too. It's mostly the shielding and distance that helps do it. So that means it is easier to remove electrons as you go down. So it's easier to remove electrons as you go to the left or down. It is harder as you go up and to the right. Alright, so continuing the PowerPoint where we left off. So let's look at potassium. Let's look at lithium. Lithium's easy. So lithium has 3 protons in the middle, has 2 electrons here, and 1 electron in the second orbit. So this is lithium, or Li. When lithium becomes an ion, how does it become an ion? Think back to when we were talking about ions. How does lithium become an ion? Remember what atoms want to be. They want to be stable by completing and having a full shell. So the first energy level is full when it only has 2, and all other ones are full when they have 8. If they're on the outer one. So when lithium becomes an ion, it's going to remove that outer shell and become lithium plus. So it's going to have a positive charge. But still 3 protons. Which atom, or which is bigger? Lithium as an atom or lithium as an ion? So lithium as an atom is bigger than lithium as an ion. As an ion is smaller. I hope this is obvious. All right. Let's look at fluorine. So fluorine, 2 electrons here, and 7 electrons here. So when fluorine becomes an ion, how does it become an ion? So to become an ion, it wants to have 8 electrons, so it gains an electron. So the only thing that happens, so here it loses an electron. Here it's going to gain 1 electron. This is where the Bohr model isn't as useful, because of my assumption I told you at the beginning. What do you think the size is going to do? Do you think by adding an electron, it's going to magically shrink and get closer to the nucleus?
Maybe ever so slightly.
Why? So we're putting them on the same ring. And this ring is, so I guess you could assume that the ring, now that has more negative charge, will be attracted. But that's not the case. Whenever fluorine becomes negative, the electrons push each other and bow outward. Think of it like this. Think about you have a rope, or really the better thing would be think about you have magnets. And you have the magnets in such a way that they repel each other. Or think about it as you have a finite rope. So we have a rope. And what I want to do is unravel this rope and fit into this rope an extra piece. And I want to make it a perfect circle. If you add a little bit more rope here, what happens to the radius of the circle?
Okay, I think I see why the Bohr model is bad. Is it equal distance between each one, so the repulsion on both sides?
Yes. So, the electrons do interact with each other, and it pushes them out. But I'm trying to think of a way of making this model useful. What ends up happening is when you insert an electron, it makes this orbit bigger. It makes the circle bigger.
It's like
And then the circle can shrink based on the strength of the nucleus. So we aren't changing the strength of the nucleus. So its effect on the ring doesn't exist. So it doesn't pull any more strongly on the rings. Therefore, adding to the ring makes the ring bigger. So when you become a negative ion is bigger, and the neutral atom, so the ion, is bigger, the neutral atom is smaller. And the reason why this is, the actual reason, is the repulsion of electrons in the same energy level. Push each other outward. This is where the Bohr model breaks down. In how I described it at the beginning. I described it as if these electrons don't interact with each other, but that's not true. The best way of thinking about this is if you are only adding or removing electrons, then removing electrons makes the atom smaller. Adding electrons makes them bigger. It's very clear that removing a whole energy level is going to make it smaller. And you can think about that. The reverse has to be that has to be the opposite. If removing them makes them smaller, then the reverse has to be the opposite. So, going back to the PowerPoint. So, how does losing or gaining an electron affect the size of an atom? Positive ions are always smaller than the neutral atom because they lose the outer shell electrons. Negative ions are always larger because they're filling up that outer shell. They're gaining electrons. They're adding to that outer shell, making the shell larger. That's another way of visualizing it. Remember that you're putting electrons into that ring, or that shell. And by filling out the shell, you have to make it bigger. And you're not changing the positive charge of the nucleus, so the nucleus isn't pulling any stronger on that shell. So as we go left to right, there's a decrease in size for positive ions. Remember, or recall from the periodic table that ions on the left side become, or atoms on the left side become positive ions. Atoms on the right side become negative ions. So this one's going to be different than the other ones because we have to break the periodic table in half. And again, we will ignore the transition metals because there are exceptions to everything. So starting in group 5, there is a sharp increase following by a decrease in the size of an anion as you move from left to right. What's an anion? It's been a while since we talked about this. This is the reason why I want to restructure the class. Because of the big gap when we did talked about electromagnetism. So remember, positive ions are called cations, and negative ions are called anions. So ion size increases as you move down a column for both the positive and negative ions. That's because as you go down, the radius is bigger. So as we go down, ion size increases. And this works on both the left and the right side. And as we go left to right, so as we go to this side, so from 1 to here, so this is positive. As we go left to right, ion size decreases. And starting with group 5, there's a sharp, so 1, 2, 3, 4, 5. So this is group 5. There's a sharp increase. So, and it goes down, it decreases like this as you go to the right. So there's a decrease too. So if you were to plot, so ignoring the transition metals, so I have hydrogen, then we have beryllium, so ignoring, then we have, ignoring this, we have boron, carbon, nitrogen, oxygen, fluorine. So this is 1, 2, 3, 4, 5, 6, 7. You really can't include hydrogen or helium. I mean, you can't really include the noble gases. Why?
Very complete.
Yeah, they don't make ions. But, so I'll remove this. That doesn't count. So starting here, if I were to plot size, they should decrease as we go to the right. And then once we get here, there should be a sharp increase. And then it should start decreasing too as we go to the right. So basically, as we go to the right, there should always be a decrease, except for whenever we transition to the the negative ones. So starting from 5 to 7, is negative. And from 1 to 3 is positive. Technically, 4 is an exception too, because they can produce either cations or anions. Usually, though, these don't react too much. For example, carbon is your pencil lead. It doesn't react too much. Diamond is carbon too. It's a different arrangement of carbon. If you arrange carbon atoms in a crystal structure, it makes diamond. If you arrange them into sheets that stack on each other, it's graphite. If you take those sheets and wrap it in a tube, it's carbon nanotubes. And if you do it in a hexagonal plane, you get graphene. Is it? Yeah, graphene, which is very strong. Ion size, I'll say this. I don't really do too much trends, other than you need to know that, so for, do I have the screen on? I don't really have this trend good. It's the reason why I'm not trying to come up with a way for you to visualize it, because I don't test on it. The only thing you really need to know about the trend of ion size is cations are smaller than their neutral atoms. Which cations meaning positive ions. And anions, which is the negative ions, are bigger than their neutral atoms. That's the only thing you have to remember about the trend in the ion size. This is useful in visualizing atoms. So if we look at salt, sodium, and chlorine. See if I can look that up. I'm curious. Sodium atomic radius. So sodium atomic radius is 180 picometers. And chlorine, I should probably put that over here. Chlorine is 100 picometers. Let's see if I can find the atomic radius of sodium ion. Which I probably won't be able to do. I'm curious of whenever these become an ion that sodium ends up smaller than chlorine. Because when they're both atoms by themselves, sodium is bigger than chlorine. But when they bond together and become table salt, sodium is going to get much smaller, while chlorine is going to get bigger. I want to say the chlorine atom is significantly bigger, but I can't find it. So atomic radius. So as an ion, so sodium plus, this should be it. (0.102 nanometers). So divide by 10, or 1e negative 12. Yeah. So as an ion, it becomes 102 picometers. And where's chlorine? And this becomes 181 picometers. And that should be negative.
So they're basically inverted.
I wouldn't say that's true of everything. My point is, by themselves, this is a much larger atom. But when you see a picture of sodium, you'll see sodium attached to a much bigger chlorine atom. That is because sodium has completely lost its valence shell, and chlorine has gotten bigger. This is only true for ionic bonding. Again, I'm not entirely. It's very hard to actually measure numbers. I wouldn't trust these numbers only in plus or minus 20 is probably a good bet, or plus or minus 10. Which finally gets us to one of the more important topics in this unit. Electronegativity. The ability of an atom in a bond to pull on the electron. Again, we're going to go into much detail on ionic bonding and covalent bonding. But it's important to understand the difference now in the context of electronegativity. So when electrons are shared by two atoms, it's called a covalent bond. When the atoms are are the same, they pull on the electrons equally. So H2 is a covalent bond. When the atoms are different, the atoms pull on the electrons unevenly. So this is like hydrogen and chlorine. So, do y'all know what some common explosives are?
Before.
C4? Let's look up the chemical formula for C4. After you get done running this. C4 is a mixture of RDX and something else, I believe. So there's actually two chemicals. RPETN. No, yeah, it's RDX, so I really need to look up RDX. Yeah. So, here's C4. Let's see if I can zoom in. So, that's way too much. That'll work. So, what do you notice about, first of all, we'll learn later on. Note, when these two lines meet up, that's a carbon atom with, what is that? Oh my goodness, I'm on a brain fart of what, the white circles are. Hydrogen atoms. You don't really need to know this. All you need to know is what's the main chemical, or what's the main element in this? It's the, nitrogen, is it? The blue. Let's look up, what's another very famous explosive? No, it burns. TNT? What do you think the N refers to?
Nitrogen.
Nitrate, I believe. Oh my goodness. Try nitroline. So if I pull up, oh, that's a horrible image. If I pull this up, we'll see nitrogen atoms again on the outside. Where are we breathing right now? What gas are we mostly breathing?
Carbon dioxide.
I hope not. That's poisonous. What are we mostly breathing in?
Oh, oxygen.
Definitely not. Did that kill you? What is air mostly made of? This should have been 7th grade science class. Definitely not. That kill you. Oxygen toxicity is bad. Definitely don't want to be breathing in pure oxygen. Air is 78% nitrogen. It's a little over 20% oxygen. O2. I think it's like 20.5%. And depending on where you live, about 1% water vapor. It's very humid. And the rest is trace gases. First of all, if you have a candle, why is there a fire burning when you light a candle? What's it reacting with? It's reacting with oxygen, right? What happens if you put a glass over a candle? It will burn through and consume all the oxygen. And once the oxygen drops low enough, no more fire. What would happen if the entire Earth was filled with pure oxygen?
Spontaneous combustion.
Not spontaneous, but basically any candle, the world burn. We breathe mostly nitrogen. which is useless. It doesn't do anything. The reason why is because there are three bond. There's a triple bond between the two nitrogen. They are very strongly pulled together. So 3 electrons from this nitrogen is shared with this nitrogen, and 3 electrons are shared with this one. If you look at the explosives, they all have single nitrogen bonds, which is unstable. Very